Okay, so we are starting from atomic structure. Basically, I will do a quick revision. You know each and everything I know, but I just want to tell you about the main points regarding the past paper and your main paper that is coming. Okay. So this is very easy, of course. Electron has a negative charge, proton has a positive charge, and the relative mass of electron is 1 over 1840. It's approximately 2000 times lighter than that of proton and neutron, right? So electron is the lightest particle and proton is the neutron is the heaviest particle. Until that, like despite they are having the same masses, but this is not an exact mass. It's a relative mass. Okay, if you will see the exact values, so they are not equal. Neutron is sometime higher than that of proton. Okay, so neutron is generally higher, so we can say that neutron is the heaviest particle. So proton number means, of course, total number of protons present in the nucleus of an atom. Okay, which is an atomic number, which is the sum of I can say the total number of electrons and protons. Generally, we use the term proton number, right? But you must know that what is the difference between these two? Only a slightly difference between the proton number or atomic number. And most of the time, we generally consider that they are the same thing, okay? Specifically, I'm saying atomic number is total number of electrons and protons, but proton number is the total number of protons. And what is mass number? Remember, mass number cannot be in decimal. Like if you remember from the periodic table, the mass number of chlorine is like if you can see the mass of chlorine, so you will see that is going to be 35.5. So what you would call at? You will say that it is going to be atomic mass, not the mass number, because this is in decimal. Mass number cannot be in decimal. Mass number definition is sum of proton and neutron. And you know that proton is always a whole number and also neutron is always a whole number. If they both are whole numbers, so the sum of whole numbers would be the whole number. So that's why mass number is always a whole number. Let's say carbon. Carbon is 12. So this is mass number because this is whole number. Okay. This is not in decimal. Okay. So mass number is the sum of proton and neutron. And how can we find out the number of electron, proton, and neutron? This is very basic topic. It's a baby topic, but I just will do a quick revision. Let's say I have to calculate the number of electron, proton, and neutron in aluminium. So this is the smaller number, which is the proton number. It would be telling you about the electron and proton. Electron is 13, proton is 13. They are always the same when there is no charge. They will be different when there would be a charge, whether you have a positive charge and whether you have a negative charge. And how can we find out the number of neutrons? So always we subtract the higher number from the smaller number. That is going to be 27 minus 13, that is 14. It's the number of neutron in the aluminium. Okay. So what if I have an ion? Ion means any charged particle, whether you have a positive charge or a negative charge. If you have a positive charge, it's known as cation, and if you have a negative charge, it would be anion. Cation is positive, anion is negative. So when element loses electron, forms cation, and when it gains electron, it forms anion. Let's say if I have aluminium plus 3. Remember, everything would be the same, but only the number of electrons would be different. Let's say in the normal aluminium, I had 13 electrons, but in Al3 plus, I would be having 10 electrons. You know why? Because plus 3 means the loss of 3 electrons. Other things would be the same, like proton would be the same, neutron would be the same, each and everything would be the same, but only the number of electrons would be different. So positive means you have to subtract electrons and negative means you have to add electrons. In the normal phosphorus, we have 15 electrons because the proton number is 15. But in P minus 3 plus 3 means I have to add 3 more electrons. So it would be 15 plus 3 is equal to 18. Rest of the things are not going to change. Proton will remain the same. Neutron will remain the same. Only the number of electrons would be different. Whether you are going to do calculation for the cations and whether you are going to do a calculation for the anions. Okay. Sometime you will see the compound ions as well. Let's say you have to tell the total number of electrons, protons, and neutrons. Let's say if I have this one. So this is sulfur. Sulfur has 16. 16. This is the proton number for sulfur, and the proton number for oxygen is 8. So what you have to do? Individually, you have to calculate electron, proton, and neutron. Let's say what I did for sulfur, this is the electron, proton, and neutron, and this is for the oxygen. And I have just added these together, and that's it. Okay. This would be the calculation for the compound ions. It's nothing new, but if you know how to calculate the number of electrons and protons and neutrons, so that would be very easy for you. And then, of course, I would not like go in detail about the shells and the orbitals and the number of particles. You know this thing, but I would, you can say, uh, tell you the main things regarding this according to your exam. So, you know, how many shells we have, it depends on the number of protons. Generally, generally in unit 1 Edexcel, we use configuration on the basis of orbital, not on the basis of shell. But you must know what is this. Let's say in the first shell, I have 2 electrons. In the second shell, we have 8. In the third shell, we have 18. In the fourth shell, we have 32 electrons. This is an old configuration that we used to do in IGCSE, right? But now we have to do on the basis of subshell and on the basis of orbital. And the concept is, first of all, we have the shells. Then in the shell we have orbital. Then in orbital we have a subshell. First of all, um, we have shell, then subshell, then orbital. Orbital is the last one. Okay. So part of shell is called subshell. It's an accurate location of an electron. Let's say if this is the shell, so where is an electron? In this area, in this area, in this area, in this area. So I want to know the exact position of an electron. That's why we are supposed to know about the subshells and also the orbitals. So how many subshells I have? S, P, D, F. S has 2 electrons. This is the maximum capacity. P has 6, D has 10, and F has 14 electrons in total. Then, of course, depends on the size. If you have 1s, so the size would be smaller. If you have 2s, so the size would be slightly higher, and so on. What is orbital? It's an area around the nucleus at which the probability of finding an electron is maximum. The region in space where the probability of finding an electron is maximum, that's known as orbital. So orbital would be giving you the very accurate location of an electron. And then this is the shape of p orbital. In most of the time, you have noticed that examiner asks the shape of s orbital or a p orbital. So you must know this, right? P subshell has 3 more orbitals, px, py, and pz. Okay. Each and every orbital has 2 electrons. So 2 plus 2 plus 2 would give you total 6 electrons. That's why we say that P subshell contains 6 electrons, okay, in total. And what about d orbital, like d subshell? You are not supposed to memorize the shape of the d orbital, of course, but you must know that d subshell has total 5 orbitals. You are not supposed to know the names. Just for your knowledge, that d subshell has further 5 orbitals. If you remember, when we used to write electronic configuration, so we used to write 5 boxes, 1, 2, 3, 4, 5. This is the d subshell, and whenever we show p subshell, we write 3 boxes. 3 boxes means what? Px, py, pz. So what does it mean? P subshell has 3 orbitals and d subshell has 5 orbitals. Okay. Or Each orbital contains two electrons, whether the orbital is of p, whether the orbital is of s, whether the orbital is of d. Okay, and then afterwards we need to write electronic configuration. This is very important part of this chapter. Electronic configuration means arrangement of electrons, and what the rule says, we have to put electrons in that orbital, in that subshell whose energy is lower, like in ascending order, not in descending order. First of all, you have to start from the lowest one, the orbital which has the lowest energy, and then move on to the one which would be having the higher energy. Okay, so other thing is that how do we know which subshell has a higher energy and which subshell has a lower energy? So we have this table. We are supposed to take help from this table. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, and then so on. School is school, public is school, public is school, doubt, public is school. S has two electrons. When I would see S, I would put 2. When I would see P, I would put 6. When I would see D, I would put 10 because I know the maximum capacities of these subshells. Okay, so I would put the numbers accordingly. I did the same thing. So energy increases from left to right. So of course, I am supposed to put electron first in the 1s because it has the lowest energy. Okay, and then move on like as the energy increases. So we are supposed to put electrons. Let's say the configuration for magnesium, the proton number is 12. It's going to be 1s2, 2s2, 2p6, 3s2. I have started from 1s2, then 2s2 because we have total 12 electrons. 2 plus 2, 4 plus 6, 10, 10 plus 2, 12. So we have total 12 electrons, right? And then what about chlorine? Chlorine is 17. So 1s2, 2s2, 2p6, 3s2, 3p5. That's the configuration for chlorine. Simple. Okay. Let's say if I have copper. So the configuration for copper would be the proton number for copper is 29. The proton number for copper is 29. So means that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. We have two exceptional cases in configuration. Number one is copper, another one is chromium. Let me tell you that. Let's suppose if I'm going to write copper, the normal and general configuration for copper is this one. Okay. But the thing is that 3d9 is neither fulfilled nor half filled. It's unstable. It's partially filled. We have to make it stable. So what I'm supposed to do, I have to just transfer one electron from 4s to 3d. It would become 3d10. It would become 4s1. Both are stable now. This is going to be fulfilled and this is going to be half filled. Both are stable, so this would be the configuration for copper. If the examiner would be asking to write down the configuration for copper, you are supposed to write down this configuration rather than this. Okay. Same goes for chromium. The proton number for chromium is 24. So for the 24, I can say 4s2 3d4. This is the normal configuration, right? Since 3d4 is neither fulfilled nor half filled, again I can say that this is going to be unstable. So how can I make it stable? So I have to just transfer one electron from 4s to 3d. It would become 3d5 and it would become 4s1. Again, I would say that both are half filled, both are stable, both are half filled and both are stable. So this would be the stable configuration for chromium. But remember, this is valid only for the copper and the chromium according to the syllabus requirement. Okay, only for copper and chromium. And one other thing that we need to know about the 4s and 3d, the thing is that the I can say the energy for 4s is higher than the 3d. Let me tell you that the energy for, like, we have these two orbitals 4s and 3d. Remember, the energy difference between 4s and 3d is very small. You can see the slight difference between the 4s and 3d. So when you will be putting electrons in 4s, and also in 3D, so there would be a repulsion between electrons, there would be a repulsion between electrons in 4s and 3D. So as a result of repulsion, 4s would feel force of repulsion. So as a result of this, the energy for 4s becomes higher. So remember, if the energy for the 4s orbital is higher, so whenever we are supposed to write down the configuration in which there would be a 4s orbital, so we are supposed to write this one, not for this, because the energy for 4s orbital is higher. So what's the order of configuration from, like in increasing order, ascending order, from the lower energy to the higher energy? Since we know that the energy for the 4s orbital is higher, so the 4s should become after 3D, isn't it? So the 4s should become after 3D. So that's why this is the correct configuration of chromium. This is wrong configuration. Same goes for copper. Again, I'm supposed to write 4s after 3D because the energy for the 4s orbital is higher. So this is not only for the copper and chromium. Whenever you can see any element in which the 4s orbital is involved, so we are supposed to put 4s after 3D because I told you that the energy of the 4s orbital is higher than the 3D orbital. Okay. I just wrote all the configurations in this way. This is the short configuration, argon. Argon means 18. So you are not supposed to write down this configuration. Okay. This is the short configuration, but you must know that what is mean by the term AR. AR means like the argon. Okay. So, and then after doing electronic configuration, you must know these things as well. Sometime it would help you in ionization energy, why the ionization energy is higher, why the ionization energy is lower, what's the trend across the period, what's the trend down the group. So the thing is that we put just we write draw these boxes. Boxes means what? If this is the subshell, so this would be an orbital. Subshell orbital, subshell orbital, subshell orbital, subshell orbital. So orbital's configuration is more clear. It would be giving you a clear picture regarding the element, whether the ionization energy should be higher and whether the ionization energy should be lower. Okay, we would use it. We would use it. So what's the rule? How do we put electrons in this? So the rule says if you have 3 electrons, how can you put these 3 electrons? So the rule says electrons should be singly filled and then doubly filled. If you are putting electrons in this manner, it's completely wrong because you have put double electrons in the same orbital. No, the rule says first you have to fill singly and then doubly. Okay. And and then we have another principle that says electrons should be in opposite spin. If they are in the same orbital, so they have the different spins, opposite spin. If they are just like that, so this would be the stable condition. It wouldn't be like that. Sorry, it wouldn't be like that, or it wouldn't be like that. They must not have the same spin. They must have a opposite spin. Okay. So I have mentioned that these are half filled. So they are more stable. Fulfilled, half filled. Fulfilled, half filled. Fulfilled, half filled. Stable, 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 stable. Partially filled, partially, all are unstable because all are partially filled. So you must know this. And what is ionization energy? Of course, you know energy required to remove an electron. So the thing is that to make it simple, to make it shorter, according to the examiner, what you need to know, the factors on which ionization energy depends. Of course, shielding effect, the size, the charge, let's say lithium and sodium. Of course, you know the size of lithium is smaller than sodium. If the size of lithium is smaller, so means that the outer electron of lithium is towards the nucleus. It's strongly attracted. If it is strongly attracted, so more energy would be required to remove an electron from the outermost shell of lithium. So the ionization energy for lithium would be higher than sodium because sodium has a larger structure. If sodium has a larger structure, so means that and ionization energy of sodium would be smaller because less energy would be required to remove an electron, right? And also, and also, you know, uh, what if we have successive ionization energy? I mean to say, magnesium has two electrons in its outer shell. So I can have the two ionization energies of magnesium. Like magnesium can lose first electron and then it can lose its second electron. The thing is that second ionization energy of any element is always higher than the first. Why? What's the reason? So the reason is that, let's suppose if I have removed one electron and let's say the energy required was 700 kilojoules per mole and it has a positive charge. Remember, when electron is removed, when electron is removed, so the size becomes smaller. This is larger in size. This is smaller in size. Positive charge means less repulsion, more attraction. It has a greater nuclear attraction. It has a greater nuclear attraction. So when it has a greater nuclear attraction, so I would say that the size becomes smaller. If the size is smaller, now it would be very difficult to remove second electron as compared to the first. So the ionization energy would be 1400 rather than 700. So that's why I'm saying when we remove second electron, it would be difficult due to less shielding. What is shielding? Repulsion between electrons. Repulsion between electrons. Remember, that's called shielding. It has 12 electrons, more shielding. It has 11 electrons, less shielding comparatively. More nuclear attraction. Size of an ion decreases. Of course, an outer electron is towards the nucleus, strongly attracted. So more energy would be required to remove electrons. So that's the reason I'm saying ionization becomes higher. Okay, ionization becomes higher uh, as we remove electron. This is called successive ionization energy. Let's say if I'm talking about aluminium, it has three electrons. It is in group three. So first of all, when you would be removing first electron, let's say ionization is 500. So the second would be 1000. So the third would be 2000. Okay. So it becomes higher. So I told you why, because the size decreases. Okay. Or, we can also tell the group number after looking at the ionization energy. How? Let's say sodium has one electron in its outer shell. Okay. This is the configuration for sodium. You have removed this one. You have removed this one. So now the configuration becomes 1s2, 2s2, 2p6. So 2p6 is more stable. It's fulfilled. You can't remove electron from this one. If you are if you want to remove still, so a lot of energy would be needed. So of course there would be a very large difference in ionization energy. So you can predict, okay, so this element might be in group 1 because group 1 has one electron in their outer shell. So they can lose only one easily. If there would be a large difference between the ionization energies, so you can predict the group number. Let's say I'm talking about silicon. It's in group 4. It has 4 electrons in its outer shell. So it can lose one, 2, 3, 4. Okay. But if you want to remove the fifth one, no, because after removing 4 electrons, its shell becomes stable. It has fulfilled shell, fulfilled structure, more stable. So then it would be very difficult to remove the fifth electron. So that's why I'm saying if you have a big difference between the ionization energies, so then we can predict the group number. Okay, these are the factors on which the ionization energy depends. Okay, nuclear charge, then shielding, then atomic radius. In short, I just wrote the relation that you must know. They are directly proportional, so ionization energy is higher. If there is more shielding means more repulsion between electrons. Electrons are going to push each other. As a result of this, the size increases. So outer electron becomes Far away from nucleus, so ionization decreases. That's why they are inversely proportional. And let's say if we have lithium, I told you that sodium. So lithium is smaller. If lithium is smaller, so ionization energy is higher. And if sodium is larger, so ionization energy would be lower. So you can see this is very important. It would help you. Okay. Or down the group ionization energy should decrease because the size increases. Easy to remove electron. Less energy would be required. And across the period, you can see the reasons. You must mention these key terms, otherwise you wouldn't be getting any of the mark in your answer. You must mention total number of shell increases, shielding increases, nuclear charge decreases, atomic radius increases. That's why ionization energy decreases across the period. And you can see this one across the period, size decreases. When the size decreases, so the ionization energy should increase because I told you they are inversely proportional to each other. If you are thinking, sir, they all are having the three shells, so the size should be the same. So why you are saying that the size decreases? Remember, I know they have total number of shells. I have mentioned that total number of shell remains same, but outer electron increases, number of proton increases 11, 12, 13, 14. So nuclear attraction increases. Nuclear attraction increases between the nucleus and outer electron. So they will be coming closer to the nucleus. That's why I'm saying the size decreases. Okay. So across the period, size decreases, ionization energy increases, but there are some exceptional cases. Magnesium versus aluminium. According to the concept, aluminium ionization energy of aluminium should be higher than magnesium, but this is not so. Why? The answer is in the electronic configuration. Let's say 3s2 and 3p1. So it's fulfilled. It's more stable. Okay. And it's having a very strong attraction towards the nucleus. You can't remove you can remove, but a lot of energy is needed. But if you can see 3p1 is the fifth orbital further away from the nucleus. It's partially filled, unstable. Less energy would be needed to remove this electron. That's why aluminium is not following the trend. Otherwise, it should have the highest, like higher ionization energy than magnesium. Okay. What about beryllium and boron? The same thing. The same thing as this one. You can do electronic configuration. You will find your answer. Phosphorus and sulfur. Phosphorus is 15. Sulfur is 16. What's the configuration? It's 3p3. It's 3p4. 3p3 means that it's half filled, it's more stable, okay, or it's partially filled, it's 3p4, okay. There is a spin pair repulsion in this orbital, right? There is a spin pair repulsion, okay. So which makes it unstable. That's why less energy would be needed. Again, sulfur is not following the trend. Same goes with this one, with this pair. So they are the same and they are the same. So you have four total exceptional cases. Okay. Isotopes, I can say it's related to mass spectrometry. Okay. It's related to mass spectrometry. So basically, same number of proton, but different number of neutron. This is the baby topic, baby definition. But the thing is that isotopes have the same chemical properties but different physical properties. You know why? Because isotopes have the same number of electrons but different number of neutrons. Okay. Uh, okay. And they have the same chemical properties and different physical properties. So you must know the reason why they are having the same chemical properties and different physical properties. Chemical property is due to the number of electron. Okay. And you are very familiar with this relation. AR is equal to isotopic mass multiplied by abundance divided by the total abundance. That is 100. It's not 100%. It's not always true that the total would be 100. Remember, okay? In some questions, like if the examiner is not mentioning that this is not percent abundance, it's only abundance, then might be possible it's not 100. So that's why it's very important point. Okay, most of the time, most of the students don't get the answer according to the marking scheme. So this is the reason. They are just thinking that always we do 100. No, this is not so. We don't always do 100. Okay. So so the so the data would be provided to you, like chlorine has two isotopes, chlorine 35 and chlorine 37, along with their abundance. The abundance for chlorine 35 is 75%, and the abundance for chlorine 37 is 25%. So they would give you the related information, and then what you have to do, you have to just put it in this formula. As we know, isotopic mass is 35 and its abundance is 75%. And then we have another isotope that is 37 and its abundance is 25%. And just I am going to add them together. Whether you have two isotopes, whether you have three, whether you have four, whether you have five, six, seven, eight, nine, 10, so on. Just you have to add them together, you would be getting your answer. That is 35.5. That is going to be AR, relative atomic mass. Okay. Or this is completely related to like mass spectrometry, of course. So we would be doing that. Okay. Let me first tell you chemical bonding. In chemical bonding, you need to know few important points like, um, let's say, ionic bonding. Of course, it's the bond between metal and non-metal. It's very clear, of course. Bond between metal and non-metal, right? Sodium chloride, let's say, sodium is a metal and chlorine is non-metal. So it's going to be an ionic compound, right? And if you can see, like let's say, magnesium chloride, again, I would say that it's an ionic compound. So remember, if you're going to draw the dot and cross diagram for an ionic compound, so it's gonna be like that. It's gonna be like that. Okay. It's gonna be like that. Not you are supposed to do like that. Okay. This is called the sharing of electron. You must not do this. Okay. Sharing is something else. Transference is something else. This is the major mistake most of the students do. So in ionic compounds, we have transference of electron from metal to the non-metal. But in covalent compound, we have sharing of electron between the two non-metals. Okay. Um, so calcium oxide is also an ionic compound. Aluminium oxide is also an ionic compound. And then how do we know which ionic compound is stronger and which one is weaker? Depends on the charge and the size. Let's say sodium chloride and magnesium chloride. Of course, sodium plus one, chloride minus one. But magnesium is plus 2. Higher the charge, stronger the force of attraction. Stronger would be an ionic compound. What if, what if, let's say I have NaCl and NaBr. In both cases, the charges are same. In both cases, the charges are same. So when the charges are same, then we have to go to the size. Since we know that the size of bromine is larger because down the group size increases, if the size of bromine is larger, if the size of bromine is larger, so I would say that it would be having the lower attraction. So yes, I would say that sodium bromide, sodium bromide would be, sodium bromide would be weaker. Sodium bromide would be weaker as compared to sodium chloride because it's due to the size. Because it's due to the size. So we have only two factors, charge and the size. Charge and the size, okay? Right? Or okay. Then, okay. Afterwards, structure of ionic solid is a giant ionic lattice structure. This is the lattice structure in which you will see a lot of cations and anions. So there would be very strong electrostatic force of attraction. So I can say this is going to be solid at room temperature. very high melting point, boiling point, soluble in water because they are polar in nature. Good conductor of electricity in molten state, but bad conductor in solid state because the ions are not free to, most of the students write free elect. Why they are good conductor? Free electrons. No, not free electrons. Free ions. Free ions, remember, okay? Not free electrons, free ions. Or then we have a dative covalent bond. You know what is this? Dative covalent bond means the lone pair is going to transfer. You can see the transference of lone pair. The transference of lone pair, or I can say, like, I'm supposed to say because it's a nature is covalent. Co means combine. Valence shells are combining. So the lone pair is sharing, but it's one-sided sharing. In a normal covalent bond, it's a two-sided, like mutual sharing. Let's say in chlorine, Cl2 molecule. Both chlorine has 7 electrons. Both chlorine has 7 electrons. So both needs 1 electron. Both needs both needs 1 electron. So if both needs 1 electron, so they are going to share, they are going to they are going to do a mutual sharing of electron, isn't it? They are going to do mutual sharing of electron. Okay, if they are going to do mutual sharing of electron, so this would be a covalent compound, but this is a dative covalent. There is a difference. They are polar. Generally covalent compounds are non-polar. Okay, so hydrogen H positive, it needs 2 electron to complete its outer shell. So nitrogen is going to give its lone pair to this hydrogen. It's going to make a dative covalent bond. So what is the condition to make a dative covalent bond? Number one, this should be like the first species is having more electrons and another species having less electrons, so that there would be sharing of lone pair from one element to another one. You can see this one. H positive needs 2 electrons, isn't it? So as we know that water, on oxygen, we have 2 lone pair of electrons. It can give its 1 lone pair to this hydrogen, to this H positive ion, and it would be forming a one dative bond. Okay, dative bond is represented by an arrow. Okay, then I have AlCl3 and AlCl3. Again, I would say aluminium has 6 electrons in its outer shell. You can try yourself. Aluminium has 6 or not. If you have any queries, so then you can ask. Aluminium has 6 electrons. It's electron deficient compound. It needs 2 more electrons. So the two molecules are combining together. You know why? Because this chlorine is giving its lone pair to this aluminium to make it stable. And this chlorine is giving its lone pair to this aluminium. So they are going to make two dative bonds, two arrows. So they are going to make two dates. So in Al2Cl6, we have two dative bonds. Remember, okay, we have two dative bonds. Remember, okay, in Al2Cl6. So you must know how to form a dative covalent bond. Let me tell you about the covalent bond as well. This is very easy, but you need to memorize a lot of, dot and cross diagrams. Then the things would be very easy for you, right? Let's say, what is covalent bond? It's a force of attraction between the nuclei and outer electron, of course. Okay, let's say we have a lot of covalent bonds, Cl2, Br2, CH4, methane, ethane, propane, butane, ammonia, like a lot of things we have, but mandatory thing is they all have non-metals, like non-metal, 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 a lot of things we have. They all have single covalent bond. They all have single covalent bonds, remember. Okay, they all have single covalent bonds. Single, 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 single. All are single covalent bonds. Okay, so um, They are double covalently bonded, CO2, O2, C2H4, and then this is going to be triple covalent bond, N2, C2H2. You can also see HCN. This is triple covalently bonded. So hopefully you know which is single, which is double, which is triple. It's a very basic thing. But if in case you are struggling with this, so you can tell me, I would be sharing another video in which I have drawn all the dot and cross diagrams in details, right? So, so, okay. Then you can see a lot of covalent like dot and cross diagrams. And this is sigma bond and pi bond. If you have ever seen this question in the recent past papers, you know, sigma bond is a stronger bond and pi bond is a weaker bond. Sigma bond is a strong bond and pi bond is weak bond. Okay, this is sigma and this is going to be pi bond. Okay, you know why? Because in sigma bond, the orbitals overlap head to head, directly overlapping with each other. And in a pi bond, they overlap side by side, side overlapping, side overlapping. And whenever the orbitals overlap side by side, so the overlapping is weaker. Bonds can be broken down easily, less energy is needed. So that's why the bond is weaker. So you must know what is sigma and what is pi bond, okay? You need to know the difference between the sigma bond or you can say the pi bond, okay? And also remember, if there is a double bond, so it is supposed to be the pi bond. If there is a sigma single bond, so this should be the like the sigma bond. So the difference between single bond or a double bond. Sigma bond is single bond and double bond is a pi bond. And afterwards, you must know the geometry. This is called valence shell electron pair repulsion theory. How do we know the shapes of molecules along with their bond angles, along with their geometry? What is this? The thing is that if you have ever noticed, whenever I ask to draw the diagram for CH4, CH4, so you will always do like that, isn't it? And we do this. This is the general thing. We do this. Technically, this diagram is incorrect. You know, the bond angle is 90 degrees. When the bond angle is 90 degrees, so there would be repulsion, isn't it? Because the electrons are just close to each other. So when there is a repulsion in a compound, so the compound becomes unstable. When compound becomes unstable, so remember, it should be it should be stable. How can it get stability? You know, they are going to repel each other naturally. Let's say if you have a four balloons and you are going to just uh, like you can say you are going to just leave that four balloons in open atmosphere in an open environment. So these four balloons will set its position in such a way that they will be as far away from each other to get stability. Just assume that they are electrons. Of course, electrons have negative charge and they are going to repel each other. Okay. So, so the compound, like I'm talking about these four hydrogen atoms. So in space, when you will see this molecule, so this molecule will rearrange itself in such a way that the bond angle becomes 109.5 degrees. At this bond angle, they have a minimum repulsion and maximum attraction. So this is more stable. Now the students ask, sir, for this one, yes, we get to know that the bond angle is this one, but what if we have any other compound? What if we have any other compound, CO2, H2O, C2H6, C2H6? What if we have these compounds? Of course, we would not be able to predict for each and everything. So we have made some rules and regulations. This is called the valence shell electron pair repulsion theory. Remember, you just have to draw the dot and cross diagram. Okay, you just have to draw the dot and cross diagram and just you have to count the bond pairs and a lone pair. And then just you are supposed to match that with this table. And of course, for that, you need to memorize this table. You need to memorize this table, okay? So if you have four bond pairs and zero lone pair, I'm talking about CH4, so the shape would be tetrahedral and the bond angle would be 109.5 degrees. And if you have three bond pairs, one lone pair, so it's going to be pyramid. Bond angle would be this. Hopefully you understood this. I would be uploading the notes, okay, on Drive link, and I would be sharing the link. Or yeah, that's it. Just you need to draw the dot and cross diagram, and then just you need to compare like the both I can say geometry and also the bond angles. Okay. Then we have intermolecular force IMF. What is this? These are two molecules. So it has three types. Number one is temporary dipole. Then we have permanent dipole, and then we have hydrogen bonding. So we have three types in total. Okay, let me tell you first the London force, temporary dipole. It's also known as dispersion force. It's also known as ID force. Generally, it is present between the nonpolar molecules. Okay, let's say if I have two chlorine molecules, when chlorine is single, it has no charge. Chlorine is nonpolar, no charge. Let's say if you are sitting alone, so you are neither happy and nor sad. Nothing, there is no one with you, of course. Sadness and happiness is related to the people. If there is no people, so nothing else. So when chlorine is single, chlorine is nonpolar. Let's say if the two chlorine molecules are coming close to each other, so there would be repulsion between electrons. As a result of repulsion, there would be unsymmetrical distribution of electron. As a result of this, chlorine would be having charge. Dipoles. The one which has more electrons due to repulsion would be having partial negative charge. The one which has less electrons would be having partial positive charge. After they got the partial charges, I can say the molecule becomes polar. Initially, remember it was non-polar. As a result of repulsion, it became polar. Okay, so this is called inter-London force, London force, and it's temporary. If you are doing, let's suppose I'm separating these two molecules. Let's say. So remember, when they are separated, again they would be at the same position, like they again become non-polar, no charge. So when they are close to each other, so there would be repulsion, there would be a dipole. I would say that's why we say it's a temporary. It's a temporary. When they are close together, there is a charge. When they're far away from each other, there is no charge. This is the reason London force is called temporary dipole for few minutes, for few hours. Okay. So London force is depending on two factors, number of electrons and the surface area. Why iodine is solid and chlorine is a gas? Because iodine has more electrons and the size of iodine is larger. So it has a more surface area. Okay. If it has more electron, if it has higher surface area, okay, so means that more electron means more attraction, and more attraction means iodine would be solid at room temperature, and chlorine is a gas at room temperature because chlorine has less number of electrons. And what if, let's say, surface area has 5 electrons in total? Again, it has 5 electrons, but the surface area for this molecule is lower, smaller. So the boiling point would be lower because IMF is lower, right? Isn't it? Surface area is higher. Surface area is higher. If the surface area is higher, so the boiling point is higher. Remember, so we have only two factors. Okay, this is related to London force. It's not a permanent dipole. Permanent dipole is present between the polar molecules. Polar molecules. Polar molecule is the one in which you can see The polar molecules, let's say HCl is polar. Why? Because it has different elements. Okay. H is different, Cl is different. It is going to be polar one. Between the polar molecules, there is a permanent dipole. Okay. Permanent dipole is stronger than the temporary dipole. Okay. Or water is also polar. So there would be permanent dipole. But Cl2, Br2, I2, H2, Ag2s, all hydrocarbons, they are nonpolar. When they are nonpolar, so it means that they are going to have only London force, okay? And when there are polar molecules, so I would say that there would be a permanent dipole between the two molecules. So you have to see first whether the molecule is polar and whether the molecule is nonpolar. If the molecule is nonpolar, so there would be temporary dipole or a London force, but if the molecule is polar, so there would be a permanent dipole, okay? So then we have hydrogen bonding, which is the force of attraction between hydrogen and highly electronegative elements. We have three highly electronegative elements: phone, fluorine, oxygen, or nitrogen. HF has hydrogen bonding. Why? Because it is fluorine. H2O, oxygen is highly electronegative because this is hydrogen bond. So that's why it has hydrogen bonding. HCl doesn't have hydrogen bonding. It has only permanent dipole. Okay, water has a permanent also and also hydrogen bonding. Hopefully you are understanding what am I saying. Okay. NH3, it has nitrogen, member of phone, it has hydrogen bonding, and also it's a polar, it has different elements, it has a permanent dipole as well. So that's the difference, okay? It's very easy to decide whether it has a permanent dipole or whether it has a temporary dipole. It's very clear, remember, each and everything is very clear, okay? So, and afterwards, I can say about the dipole moment. That is also the very important topic in this one. If you have ever noticed, let's say carbon dioxide. Is this polar or non-polar? CO2. Let's say if I have a chair and okay, I have a chair. Let's say if this is you, okay, and this is me. I'm applying the force of 5 Newton and you're also applying the force of 5 Newton. So the chair will not move. The chair will not move because the forces are cancelling each other, isn't it? The chair will not move because the forces are cancelling each other. That's why the carbon dioxide is non-polar. Okay. But the bond is polar. Remember, I'm using the two terms. The bond is polar due to the different elements, but compound is non-polar because they are cancelling each other. Hopefully, you are understanding what I'm saying. The bond is polar, but the compound is non-polar. What if I have CH4? Same. They are going to cancel each other. The compound is non-polar. What if I have, what if I have this one? Due to this chlorine, it becomes unsymmetrical. So this is polar because they're not canceling each other. Okay. So you have to check. You have to check. This is known as dipole moment. This is known as dipole moment. Remember. Okay. So you can go through this and inshallah in the other part, I would be revising the remaining chapters and that would be fine for you. So what we did today and what is remaining, we did atomic structure and the periodic table. Okay. And we did chemical bonding as well. Okay. Or organic chemistry is remaining. Okay, organic chemistry is remaining, inshallah. I need one more part, so you will see another part soon. Most probably, inshallah, tomorrow morning. Okay, ji. Thank you.